All right, everybody, we're going to take those relationships between the variables that we just learned about and apply some mathematical relationships now. So the first one we talked about was pressure and volume being inversely related to each other. And inversely related mathematical relationships look like this. It's P1 V1 equals P2 V2. Basically, as pressure goes up, volume goes down, and as volume goes up, pressure goes down. So this is an inverse relationship, and this is how the math looks. The next is pressure is directly related to temperature. So when one goes up, the other also goes up. And we learned about that relationship just recently. Mathematically, it looks like this. P1 over T1 equals P2 over T2. So if you have a pressure and a temperature and you change the pressure, the temperature is going to have to go up proportionally. Next, we've got volume is directly related to temperature. It looks a lot like the one that we just did right above it. But instead of pressure on top, we have volume on top. So it looks like this. V1 over T1 equals V2 over T2. Now this next one is the amount of particles is directly related to volume. And so we have N1 over V1 equals N2 over V2. So when you increase the number of particles, the volume will go up proportionally. Now these last two, we'll take a look at pressure and amount, and just like amount and volume, it's directly related. So if you got N1 over P1 equals N2 over P2. So if the number of particles goes up, the pressure has to go up proportionally. Finally, the amount is inversely related to the temperature. So that looks like this. N1 times T1 equals N2 times T2. So if you take a number of moles and you increase it, then the temperature has to decrease proportionally in order to keep the volume and the pressure consistent. So these are the different relationships between two variables, and now we're going to put them all together in what is known as the combined gas law. So if we take all of those formulas on the last page and we combine them all together, we get one overall derived relationship. This is what is known as combined gas law. You can see it over here. It's P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. This formula is used whenever you have a situation where you've got a sample of gas and you know all the variables to start with. Those are all the initial set of situations. And then you start to change the variables and you can solve for one of the missing P, V, N, or T variables. Now sometimes you solve for one of the two variables, the things that are after the change, or sometimes you solve for the one variables. Maybe I give you all of the conditions of how it ends up and ask you, well, what was the initial pressure if this is now true? And so this formula that has N1 and N2 and P1 and P2 and all the variables can be used to solve math problems where we basically set up a problem and solve for the missing variable using algebra. Any variable can be held constant, and if so, it can be removed from the equation, because if it's the same on both sides, we can essentially cancel it out. And so that helps save some confusion. Maybe just cross it out or don't write it in because it's being held constant. Now, oftentimes we don't change the amount of gas particles. Sometimes we do. Sometimes that N number does change, but oftentimes it isn't. And so usually we will see the combined gas law written like this over here, where it's just P1 V1 over T1 equals P2 V2 over T2. As you can see, because the number of particles is held constant, then we just exclude it from the combined gas law. This is how you will see it written in a textbook most often. So let's do a couple of examples where we can put that combined gas law into practice. Let's take a look at this first one. It says gas in a closed balloon, which means that the number of particles is held constant, has a volume of 7.5 and a pressure of 111 kPa. What would the volume of the balloon be if we reduce the pressure to 45 kPa? And so if I'm going to take P1 V1 over T1 equals P2 V2 over T2, and I just plug in everything I know, well, I can take the 7.5 liters, that's my initial volume, and I can multiply that by 111 kilopascals. Now, assuming constant temperature, we can then solve for a missing volume, we'll call that X, if the initial pressure is 45.0 kPa. We already talked about how the number of particles, because it's a closed balloon, is being held constant, but we can also talk about the temperature and how it's being held constant, so we can just cross it out. So using basic algebra, you solve for X, and you get an answer of 18.5. Now the label there has to be the same as the volume, and that should be in liters. So significant figures also comes into play. Since all these digits have 3 significant figures, then my answer is rounded to 3 significant figures, so my final answer is 18.5 liters. Let's read through this next one now. 25 moles of oxygen gas has a volume and a temperature, and it's in a flexible cylinder, so that means that the volume may change. It maintains a constant pressure, so we'll make sure to take pressure out of the formula. What would the volume be if you reduce the gas to 5.0 moles? So this is one of those situations where we talked about on the last slide where I usually keep the number of moles constant, but this is an example where you don't. So I'm going to include the number of moles. So I have volume 1, but pressure is held constant over N1 times T1, and that's equal to V2 times N2 over T2. Now remember, I'm not including the pressure because once again it's constant, but that would usually go in the numerator next to the volumes if it was included. But this is the combined gas law without the pressure. So I'm going to put the volume, which is 24.0 liters on the top, and the number of moles is 25.0, and the temperature is in Kelvin. And I talked about this in a previous video, but we always want to change our degrees Celsius to Kelvin. So if this were degrees Celsius, you would add 273 to it. But since it's already in Kelvin, we don't need to worry about changing it. In combined gas law problems, I always do the temperature in Kelvin. Now I'm going to set that equal to the new volume, which is X on top, if it was reduced to 5 moles and the temperature was increased to 400 Kelvin. Now I'm going to do algebra, do a little cross multiply and divide, and solve for X, and I get a correct answer of 10.97, and I'm going to round that to 3 significant figures, or 11.0 liters. Now let me scroll up a little bit to give myself some room for this last one. But it says the pressure of the set amount of gas, so that means that the moles of gas is going to be constant, in a flexible 2.25 liter container is at 25.5 atmospheres and a temp of 373 Kelvin. The container can hold the pressure up to 100 atmospheres before it will burst. Assuming the volume will expand to 2.50 liter, what's the maximum temperature you can reach before it will burst? So this time I'm solving for a temperature. So I start with the 2.25 liters, and its pressure is 25.5 atmospheres. So that's my P1 and my V1. And I'm going to set that over T1, which is 373. Now set that equal to, it says it can hold up to a pressure of 100 atmospheres before it will burst. Assuming the volume can expand to 2.50 liters, solve for X. So solving for an unknown in a denominator is kind of tricky, even for advanced math students. Sometimes a student will try and solve for a variable in the denominator and screw it all up. So I do recommend a cross multiply and divide in this case, and then that would basically avoid any mistakes when solving for an unknown in the denominator. When I do this, the temperature is 1,625 Kelvin. And I want to round that answer off to only 3 significant figures. So I'm going to round it off to 1,630 Kelvin. So my temperature can get really, really high before it explodes. Well, that is a rundown of what combined gas law is and how it's used to do math problems where we solve for a missing variable. I hope this was helpful. That takes care of this video lesson. Thanks for watching.